Today, we're going to cut through all the noise and look directly at the data. We're going to piece together the story of our planet's changing climate, one number, one chart at a time. So, what is the real story here? That's the big question, right? We're going to unpack it together by looking at what's been happening recently, how our planet's natural systems work, and even what the deep, deep past can tell us. All right, let's kick things off with the most recent chapter of this story. This is the stuff that's happened pretty much within our lifetimes, and it shows a really clear, really dramatic shift in our atmosphere. Okay, check this out, because what's so wild about this slide is just how huge this jump is. Back in 1958, atmospheric carbon dioxide was hanging out around 315 parts per million. Fast forward to 2020, and it shot up to 420. You know, this isn't just a tiny little wobble. It's a massive, super fast increase. So what happens when you do that? Well, what happens is things get warmer. The data shows a pretty clear connection. As those CO2 levels have gone up, so has the planet's temperature. We're talking about a 1 degree Celsius increase in the global average. Now, 1 degree might not sound like a lot, but for a whole planet, that's a significant fever. But, how does one actually cause the other? It really boils down to a simple idea. Think of CO2 like a blanket for Earth. The more CO2 you add to the atmosphere, the thicker that blanket gets. It traps the sun's heat that would normally bounce back out into space. So, the thicker the blanket, the warmer we get. It's a fundamental piece of how our climate works. So to really get what's going on, we have to look at how Earth handles carbon all on its own. The planet has this incredibly complex system for moving carbon around between the land, the ocean, and the air. Let's take a look at how that whole balancing act is supposed to work. And this whole system, it's got a name, the carbon cycle. It's just this constant journey of carbon atoms moving through different storage spots, or reservoirs. The planet is always shuffling carbon around, and the speed of that shuffle is absolutely crucial. And here's the thing, it's not all one speed. You can think of it like two different gears. You've got the fast cycle, which is all about life. Plants breathing, things decomposing, that's a really quick turnaround. Then you have the slow cycle. This is geological. It's carbon getting locked away in rocks and soil for thousands, even millions of years. For most of Earth's history, these two gears worked in harmony to keep things in balance. Here's a perfect example of that fast cycle in action. A forest is basically a giant carbon sponge. Through photosynthesis, trees are literally pulling CO2 out of the air. They use that carbon to build their trunks, their leaves, their roots, and they store it in the soil. They're actively keeping it out of the atmosphere. Now let's talk about scale for a second, because the planet's natural systems move an unbelievable amount of carbon. Every single year, about 92 gigatons, that's 92 billion tons of carbon, get swapped between just the ocean and the atmosphere. This is the natural, balanced rhythm. But here's the kicker. This is the crucial point. Human activities are adding about 9 gigatons of extra carbon into the atmosphere every year. Now you might hear 9 and think, well, that's way smaller than 92. And you're right. But the problem is, it's a one-way street. It's a deposit into the system that the natural cycle just isn't built to handle this quickly. It's throwing the whole budget way out of whack. Okay, now that we kind of get the mechanics of it, let's zoom out. I mean, way, way out. Scientists can actually look back in time by studying tiny air bubbles that got trapped in ancient ice, giving us this incredible record of our planet's climate history. And when we look at that incredible, long history, we see something amazing. For hundreds of thousands of years, through ice ages, through warm periods, Earth's climate followed this predictable rhythm, a pattern held steady. And the heart of that pattern is this direct, undeniable link. The data from those ancient ice cores is crystal clear. When CO2 levels went down, so did temperatures. When CO2 levels went up, temperatures went right up with them. For nearly 1 million years, the two have been dancing together in perfect lockstep. This slide right here really puts our current moment into perspective. I mean, let this sink in. For 800,000 years, CO2 in our atmosphere cycled up and down, but it never, not once, went above about 300 parts per million. And today, we're at 420. We have completely broken out of the natural pattern that has governed our planet's climate for a truly immense amount of time. So if we know the physics and we know the history, how do we figure out where we're headed? Well, that's where climate models come into play. There's these incredibly powerful tools that let us project what could happen based on the path we're on.
Now, these models aren't crystal balls, right? They're really complex simulations that run different what-if scenarios. And the biggest what-if, the main variable that really changes the outcome, is us. It's what we humans decide to do about our greenhouse gas emissions in the years to come.
So let's just look at one possible path. In a scenario where we continue with high emissions, the models project that by the year 2100, we could be looking at CO2 equivalent levels, that includes other greenhouse gases too, of around 800 parts per million. That's almost double where we are right now. And the temperature change that comes with it? Another 2.4 degrees Celsius of warming. And that's really what it all comes down to. The data tells us the story of how we got here, and the physics explains how it all works. The models, they just show us the possible destinations ahead of us. The data doesn't make the choices. We do. So the final question, the one this whole story leaves us with, is which future are we going to write?